My name is Liisa Hirvonen. Me and Klaus Suhling will tell you about our work with Zdeněk Petrášek and Beeby on time-correlated single photon counting microscopy with an image intensifier and ultra-fast camera.
Photon counting imaging was originally developed for astronomical applications, but this technology can also be used in other fields. Here we show that photon counting imaging can be used on a fluorescence microscope to map the lifetime of dyes in living cells. This technique is independent of the probe concentration, and the point of the lifetime measurement is that the lifetime is an indicator of the photophysical environment, for example the oxygen concentration.
With camera-based single photon counting, we record images of single photon events, shown here on the left, and find the centroid positions, shown on the right. We do this to every frame and then adapt the frames. The more we add them, the clearer the image becomes. The final image shown here contains around 300,000 photons, but for lifetime imaging we also need to find the arrival time. This is our setup. It's a standard inverted microscope with a pulsed laser at the back to illuminate the sample. On the output port we have an image intensifier and two relay lenses to image the screen of the intensifier onto the camera. The camera is not sensitive enough to detect single photons, so we use the intensifier to amplify them. In the intensifier, a photon hits a photocathode and creates a photoelectron. The electron is multiplied as it travels through the microchannel plates, and finally the electrons are converted back to photons when they hit a phosphor screen. Although the transit time spread for the electrons is small, the phosphor screen has a long afterglow. We can use this afterglow to find the arrival time of the photons. If we choose the camera frame rate so that we can see the photon events in many frames, and a photon arrives at the beginning of a frame, most of the intensity is in the first frame. As the photon arrival time increases, the intensity decreases in the first frame and increases in the second frame. To quantify this, we place a laser pulse at the beginning of the frame, measure loads of photons, and plot a histogram of the intensity ratio of the first two frames. There is a peak at the laser trigger position, and we mark the peak position on a graph of ratio against the laser trigger time. Now we move the pulse towards the end of the frame, the ratio changes, and we get a plot of ratio against arrival time. We can fit a function to this graph and use it for converting any measured intensity ratio to arrival time. We've then used this technique to measure some samples. Here's an intensity image of beads with different iridium compounds in them. The image is built pixel by pixel as shown before, but now we also have a histogram of the photon ratios for each pixel of the image. We can then convert the ratio to time using the method conversion function. The result is a normal time decay that we can fit with an exponential function to find the decay time. We do this to every pixel of the image and color code the decay times to get a lifetime image of the sample.
In conclusion, we have shown that we can exploit the phosphor decay of the image intensifier screen to perform photon arrival timing well below the camera exposure time. We have used this method to map microsecond decay times of transition metal compounds, including ruthenium-based oxygen sensors in living cells, within a few seconds. Find out more about this work in our paper in the New Journal of Physics.